from Surfax, Andrea Piacentini, Anthony Weaver, and Céline Meguerol, and from Météo France, Olivier Goux. So we are working on accounting for correlated observation error in variational ocean data assimilation. So I will start with a quick example of the SWOT mission, actually, because it's a very good use case to illustrate what happened with observation error correlations when they are not accounted for. So the SWOT mission is a mission that was launched last December, actually, and it is a mission that is designed to observe the ocean. It's a new generation of altimeter. So what it does is basically it scans the sea level anomaly or the sea surface height, and it does so with a wide swath, which is 100 kilometers long, as opposed to previous altimeters, which only measured 1D measurement as a nadir. So this is a very new and exciting technology because it will largely increase the resolution of the observations, but it also brings a new error budget that is quite new and most importantly contain large correlated errors. So I'm going just to show some results from a study from Robert King and Matt Martin from Met Office, which did a very interesting OSSE using SWOT measurements, so in a regional configuration. So what's interesting in this study is that they both try to simulate SWOT observations with white noise only and with a full error budget as predicted by the mission requirements with large error correlations. And while estimated with white noise only on the simulation, the SWOT observation largely increase compared to the control run. So they would have a very good impact on the system. While when we assimilate them and simulate them with large correlated errors, which are probably a little pessimistic in the simulator, but still more realistic, we see a very large degradation of actually the analysis. It's because of all these error correlations which are neglected. And they manage in their article to limit this negative impact by doing thinning, averaging, and only taking part of the observation on the inner swath of the satellite, but it also negated most of the positive impact. So this is a very good example of why we need a method to account for observation error correlation in data assimilation, because all this generation of new measurements, which will be at very high resolution and very informative, will not be usable as is or to their full potential without some new methods. So just to introduce a few concepts, we did part of our study in a very simple toy system and part of our study in the realistic system of NIMVAR. So for the toy system, it's a very simple framework when we have just 1D periodic domain, a regular model and observation grid, and spatially constant covariance parameters, so spatially constant variances and correlation X scales. So this is very idealistic, of course, but it's just to gain some insight on the system that we then can carry over eventually in the real system. So what's interesting in this very simple system is that the covariance matrices, B and R, are circulant matrices, meaning each line or each column, because they are symmetric, is just a periodic permutation of the previous one. It's also the case of H-BH transpose, if H is just a simple selection operator or just a simple interpolation with regularly spaced observations. And this is very interesting because it means that all these matrices are all diagonal in a Fourier space. If F, this matrix here, is a Fourier transform, represented for a direct Fourier transform, then all these matrices are diagonal in the same space, which greatly simplifies the analysis of the blue equation, for example, because everything becomes diagonal. And this is a very good way to interpret what's going on actually what we observe with observation error correlations. So if we denote epsilon O the observation error, then R is the expectancy of epsilon O transpose. And we can see very quickly that applying this Fourier transform of both sides, we can see that the eigenvalues of R actually correspond to a sort of variance of the error at each spatial scale. So it's the variance of each component of the Fourier transform of the observation error. And this is how we will interpret this error variance at scale per scale. So if we plot the background error, observation error in this spectral space, so the eigenvalue of these matrices. So here in black, you have the eigenvalues of H-BH transpose, so this will be the background error projected in observation space. And we have also a true observation error. So when I talk about true observation error, I mean the actual observation error of the observation. And we have some observation error model, which is how we account for this observation error in DA through R. So the true observation error is not generally known or not necessarily, it's hard to estimate. and the two can potentially differ. So in this example, the true observation error is correlated, which means that we have this typical spectrum in green that is decaying, which is we have less and less power, less and less variance as we go to smaller spatial scales on the right. And if we account, if we use the diagonal R and DA, then we will just replace this green curve by the blue curve, which is just a flat spectrum. We act in DA as if the observation error was just white noise, which means that we underestimate the observation error at large scales and overestimate it at small scales, which means we overfit the observation at large scales and underfit them at small scale, which means we might extract too many bias for the observations and we might not extract small scale features which will be relevant in the observations. So what we suggest to avoid that is to use diffusion operators. So diffusion operators are already used to model background error correlation for the inversional DA system, in ocean inversional DA system, such as NIMOVAR, which we have done our study in. And so it's already operational, but for background error correlations. But what is interesting with these diffusion operators is that we actually apply B by working through B-1 in a sense, because we use an implicit diffusion scheme to model it. So what happened in a correlation operator with the diffusion operator is that we have an input vector, we can see on the left panel, that is then smoothed by diffusion, by a diffusion operator, and then normalized to regain unit amplitude, which means that this whole operation is equivalent to applying a correlation operator. And this is very interesting because in order to apply diffusion to this input vector, we use this implicit scheme, which means that we solve a lot of systems. So doing the inverse of that is actually easier than doing the correlation operator itself. It means it's much cheaper actually. So the inverse correlation operator will be easily accessible, which is very interesting for R-1 because we need R-1 only in DA, variational DA. And another good point for diffusion operators is that they can be used on a mesh. Classical diffusion operators for background error correlation used on a grid, and a lot of methods need a structure. This one doesn't, because if we use finite elements for modeling diffusion, then we don't need the observation to be structured. This was actually developed during Olivier Goux' PhD at Surfax. So here I'm showing in the figure in the middle the swath that goes over the Solomon Islands, and you can see that it creates, for example, a gaps in the data. And we can see on the right the corresponding mesh. We just adapt to the gap, and which makes this lack of structure and this gap transparent in the modeling of diffusion and in the correlation operator. So we have two kind of parameters, I would say, for diffusion. So we have length scales, which are denoted D in this presentation for daily length scale, and they kind of tune the horizontal stretch of the correlation function. And we have a smoothness parameter, which corresponds to the number of diffusion iterations that we do, which is called M. And they are illustrated on the panel A and C of the figure on the left in physical space. So D is really horizontal stretch, while M, a low value, would go for a sort function, which are more weight on the tail of the distribution, while a high value of M tend to a Gaussian function. But it's very interesting to look at this function in a Fourier space, in a scale per scale, because of this analysis, we did scales per scale. So the length scale D would tune where does the spectrum cut off, where does the spectrum start decreasing in a sense. So it just shifts the spectrum left and right. While M, which is not necessarily very impressive in physical space, does something very interesting in Fourier space, in frequency space, where it changes the slope of the spectrum after the cutoff. And this is very interesting for us and very meaningful for us, actually. And also the diffusion tensor, which is used to represent the length scale, is variable, varying in space and anisotropic, which gives us some flexibility to fit the observation error correlation. So I'm showing on the left correlations that are sampled from the SWOT simulator, actually. So simulated observation error from using the SWOT simulator from GPL and CNES. And you can see on the right the equivalent model, diffusion model, which is close enough at least for our purposes. So we did implement this operator in NIMOVAR to try to confirm any insight that we gained from the toy system. And so this is implemented in Fortran in Nimovar, available in parallel. So we did start, however, with nadir altimeters, so classical conventional altimeters. First of all, because the data is already there, so it's already a lot of studies on this data, so it's very interesting for us to gain insight. But also because, first of all, the meshing and partitioning of one-dimensional observation is more straightforward at first, because we want this method to work in parallel. And there's already a lot of insight to be gained from this simpler setup, and already some operational maybe use for this. So the observations are really represented as a long line. We don't model correlation on the sphere for these altimeters, but actually just consider a long, very long line of the satellite track going around the Earth, because the correlations are mostly along track. They depend on the observation. The observation is mostly linked to the next observation, and not necessarily at crossover points. And so we have one big single block in R for each instrument. For example, JSON2 or NVSAT here, we don't separate observation correlation between time steps of the model, because observations are correlated between model time steps in the first place. So there is no meaning necessarily in having sub-blocks per model time steps, and this will be actually an additional constraint on the system, more complex to implement. So we just have one big block for the whole assimilation window per instrument. So what does this experiment in Nimovar look like? So we first started by doing experiments in the real system, so in a global configuration of Nimovar, but with synthetic data, because we wanted to be experiment with different kind of observational correlation and how we could account for them, and try to gain some insight also on future missions. So we use the square roots of B and R to generate some samples of background state and observations error, and which with respect to a known true state, and we simulate this background and SLA observations, and then assimilate them with possibly different error statistics than the one we used to simulate them, to see what happened when we use the wrong statistics. Is it bad? What happens in the system? So the minimization algorithm is a BIP recognition conjugate gradient, denoted BPCG here, and the observation are simulating using B, which is the true background error. We usually use the same background error for assimilation and error simulation, and R tilde for the assimilation. So I use the tilde to denote parameters that are used in practice in data assimilation and might differ from the true error parameters, which are used to simulate observation error. And the two can potentially differ. So I'm showing here the energy norm of the analysis error, which can be computed in this storage system because we have synthetic data, which is estimated at each iteration of the BPCG from the sample of solutions. So basically, this shows what analysis error we will get if we stop the algorithm at this stage. So in this first example, I'm using just true error parameters, a diagonal R, so the observation error really is white noise. And as assimilation parameters, we have the accurate R matrix, diagonal as well. And so just to show you what is in the curve below. So on the left panel, you have an analysis per variable, error per variable, so SSH, temperature, salinity, and the zonal and meridional component of the velocity. And on the right, you have the total error, and the field data error corresponds to the 75% quantile and 25% quantile.
You have 5 minutes, Olivier.
Oh, thanks. So we can see that, first of all, we assimilate only SLA data in this small experiment. So the SSH is the measurements that is the most improved. And there is a very low balance with salinity, for example, which is not improved by much, temperature little, and the velocity is actually slightly improved. So now, what if we have observation error correlation in our simulation? So we assimilate observation with correlated observation error. And this is simulated using parameters that which he estimated from altimeter's errors. So using, again, the SWOT simulator to look at the observation error specification of nadir altimeters. So with a length scale of 140 kilometers and a Sohr function, which is what's associated to m equal 2. So first of all, what happens if we use a diagonal R to assimilate this, which would be, in a sense, what happened operationally. We have observation which are really at with correlated observation, and a diagonal R. So now it's a naive diagonal R, which only uses the actual variance of the observation. And what happened in this setup, we can really see that we have degraded the analysis in this example, because we are looking at the analysis error normalized by the background error, and you can see that you have a 25% increase of the error on the SSH, for example, And this is because of the overfit at large scale that we mentioned earlier. We really overfit a lot the observation at large scales, and we extract too many biases from them. So this is what's dangerous with using a diagonal R. Now, in practice, in a real system, there is variance inflation that's used to avoid this kind of issue. So if we go back to this scales per scale analysis, for example, to try and understand what happened with variance inflation, actually, variance inflation will be moving from the blue model that we have here to the red one. So we just increase the variance at all spatial scales. So what this does is that it reduces the overfit at large scales, which is very important because errors are large at these spatial scales. But it's done at the expense of these small scales. So this means that we increase even more the underfit at small scales, and we might not extract even less small features for the observations, which is a shameful high resolution observations such as what to come in the future. So, and when we use this inflation, so I try to compute the optimal variance inflation factor in this case, and to see what happened. And we can see that we actually do manage to have an increase of the analysis, an improvement of the analysis. And it's interesting to notice now that U is actually very well improved by the assimilation of SLA data, now that we have observation error correlations. And the reason for that is that if the observation error is correlated, then it's lower at small spatial scales, which means that gradients in the observation are more accurate than absolute values in a sense. Which means that through geostrophy balance, actually this the meridional component, zonal component, sorry, of the velocity is well improved actually by the assimilation of SLA observation when there are observation error correlation, because we have accurate gradients. Now, what happened when we move to actually modeling using an accurate R in the assimilation with properly a non-diagonal R with properly specified parameters? So we are doing slightly better actually than the best possible inflation, variance inflation. So this means that this non-diagonal R outperforms any diagonal R, which is good for us, which is what we hoped for. But it's interesting to note here that something that we feared from using a non-diagonal R will be a delay in convergence, an eventual delay in convergence, and this does not happen. And actually, if anything, we see actually a speed up in convergence, because we showed in some theoretical papers that we already have that in this case we reduce the condition number of the Hessian matrix. So the Bieber condition conjugate gradient become more efficient. So with realistic parameters, we can already see that we expect an improvement with using this non-diagonal R, and we do not break the data assimilation system by introducing this non-diagonal R. And just a last look on the SSH increments. So on the top left, you have the ideal increment. By ideal increment, I mean the increment that would totally negate the error and make the error zero everywhere. We have a diagonal R on the top right, which is just this increment, which is too large. You can see the scale on the color bars. And we have, with an inflated diagonal R, something that is too smooth, which reduces in amplitude, but too smooth. And with the accurate non-diagonal R, you can see that it put more emphasis on small scales around the equator, which are present in the ideal increment. So it allows the extraction of small scale without an excess of large scales.
Olivier, you are at the end of your time.
Oh,
so if you can wrap up, please.
Oh, sorry, thank you. Yeah. So just quick summary, neglecting observation error correlation in the air, we have an overfit at large scales and an underfit at small scales. With variance inflation, we can mitigate that, but we prevent the extraction of small-scale features. We plan to use diffusion operators to avoid this issue because the inverse is available, it can be used for unstructured data. We have already implemented it in NIMOVAR for Nadia altimeters, and there is no delay in convergence that we use. And we plan to actually extend that to a larger correlation with Atlas, thanks to the William Deconnect from ISDA. So thank you for your help. And thank you for listening.
Thank you, Olivier. That was very interesting. And actually, if I can comment, I mean, this looks like an application that is almost ready to be used with real observation and actually have an impact on operational systems. So, so yes, I mean, we are running a bit late. So in the interest of time, I suggest you also go to Yopad to answer questions that the audience might have for you. Thank you, Olivier.
Thank you.